Do you know that understanding memory management can help you solve a wide variety of optimization problems in Spark? So, memory management has been a crucial topic, a tricky topic for most of us to understand. But at the same time, it is very important in order to develop a solid grasp over two things. The first one is how Spark works internally, and the second one is which portion of the memory is responsible for storing what. So, I'm going to make all of this very easy for you to understand, hopefully, in this video. So, let's get started. So, we are going to talk about these three topics in the video. The first one, of course, is going to be executor memory management. The second one is going to be unified memory. What is unified memory? Why is it even called unified? The third one is off-heap memory, the least talked about and often the least used memory, but it can be very useful in certain situations. Okay, so now let's deep dive into the executor memory layout. So here we have a Spark executor container, and we see that there are three major components of memory, right? The first one is the on-heap memory, which occupies the largest block over here. The other one is the off-heap memory, which is this one, and the last one is the overhead memory, right? So an important point to note is that most of Spark's operation is run on the on-heap memory, which is managed by the JVM. So for those of you who don't know what the JVM is, the JVM stands for Java Virtual Machine, and it's like a virtual computer that is used for running Java programs. So Spark is written in Scala, which runs on the JVM, but JVM serves as an execution environment not just for Java but also for other languages including Scala. So when you're writing code in Python using PySpark, you're basically what you're doing is basically you're using a wrapper around Java APIs of Spark. Yeah. So you're using a wrapper around Java APIs of Spark. And this is essentially done to be able to use all of the features of Spark. But the underlying execution that happens is still going to happen on the JVM. Yeah, it's still going to happen on the JVM, and that is the reason why on-heap memory is managed by the JVM. So the on-heap memory is divided into four sections, right? The first one is execution memory. Execution memory is the place where your joins, shuffles, sorts, and aggregations happen, right? This is that portion of the memory. The other one is the storage memory. The storage memory is the place where your caching happens, right? And this caching can be either RDD or data frame caching, right? And it's also used for storing broadcast variables. Now, this portion of the memory together is called the unified memory. It's called the unified memory. We'll come into more details regarding why it's called the unified memory, but for now, we'll cover the other parts. So the third part is user memory. This part of the memory is basically used for storing user objects, basically the variables or the collections like lists, sets, dictionaries that you define in your program, or even for storing UDFs, user defined functions. The last one is the reserved memory that Spark needs for running itself and for storing internal objects. The overhead memory, if I were to just simplify it and say it is used for some internal system level operation. And the last bit of it is the off-heap memory. Again, we are going to cover this in a lot of details going ahead. Okay, so let's take an example to understand which portion of the memory is going to occupy how much of space. Yeah, so let me quickly remove all of this, and let's assume that when we ran our Spark jobs, we specified the executor memory 10 gigabytes, right? So basically essentially this value that we specified, spark.executor.memory, we specified it to be 10 gigabytes, right? Now there is a value which is called spark memory fraction, and that defines how much of space this execution memory is going to take from here to here, right? And that is simply zero point 0.6 of the total value, zero point 0.6 of 10. So it is going to be zero point 0.6 into 10 gigabytes, which is 6 gigabyte. Yeah. So this whole portion from here to here is going to be 6 gigabyte. Now, in order to calculate how much the storage memory is going to be, you have another parameter which is spark.memory.storage fraction, and this can be adjusted based on needs, but the default is zero point 0.5, so that would simply mean half of 6 GB, which is going to be 3 gigabyte. Yeah, and this is going to be 3 gigabytes because 6 GB minus 3 GB, 6 GB was the total from here to here, and this one is 3 gigabyte. So the remaining is 6 GB minus 3 GB, which is 3 gigabyte. Yeah. Now this portion, this whole portion that you see is 10 gigabytes minus 6 gigabytes, because 6 gigabytes was this portion, right? So this is going to be 4 gigabyte. This whole portion is going to be 4 gigabyte. Now if we want to find out how much is the user memory from here to here, this is simply going to be 4 gigabytes minus 300 MB. And for simplicity, let's assume that 1 gigabyte equals 1000 MB. This is simply going to be 3700 MB, which is 3.7 GB. Yeah. And the last one, as we already know, is 300 MB. Yeah. So these are the final values that you would have when you were to allocate memory within a cluster. Yeah. So again, just to reiterate, your whole size was 10 GB. You ended up having 6 GB total over here, which is from here to here. Now this portion of the memory occupies 3 gigabytes. This also occupies 3 gigabytes. And this portion, this whole portion is 10 gigabytes minus 6, which is 3 plus 3. So this is going to be 4 gigabyte, this whole portion. And to calculate the value only for this one, you just have to do 4 gigabytes minus 4 gigabytes minus 300 MB, which is 3.7 GB. Yeah. So that is how the calculations are going to look like for the on-heap memory. Yeah. Now, when we define executor memory, this is completely separate from the off-heap memory and the overhead memory, right? No portion of memory that we define over here is going to be allocated over here. Yeah. So if we wanted to calculate the overhead memory, the overhead memory is simply defined by maximum of 384. So it's maximum of 384 or 10% of Spark executor memory. So Spark executor memory is 10 GB, 10% of it is going to be 1 GB. So maximum of 384 and 1 GB. 384 MB or 1 GB, and this is going to be 1 GB. So your overhead is going to be 1 gigabyte. And coming to the off-heap memory, the off-heap memory is disabled by default. So you see that this parameter over here is set to 0. You can of course set it to a non-zero number and basically, let's say, allocate memory over here. But the way off-heap memory is structured, this also has two parts. The first one is execution and the second one is storage. So it looks the same as this one, as unified memory. Yeah. So normally it's disabled, but if you want to use it, you basically have to go ahead and set this. A good start can be something like setting 10%, 10 to 20% of your executor memory. So 10 to 20% of this 10 GB, which is the executor memory, you can set this value and start experimenting around this, right? So now one possible question that you may have is, the executor memory is 10 GB, but 10 GB is only allocated to this portion of the memory, right? So how does these two portions get memory? Like, how is memory allocated to these two portions, right? So a very important point to note is that executor memory allocates only for on-heap, and when Spark requests the cluster manager such as yarn for memory, what it is going to do is that it is going to add the executor memory and the overhead, and if off-heap memory is enabled, it is going to add that, and then it is going to request yarn for memory. So in this case, I assume that off-heap memory is disabled, overhead is 1 GB, executor memory is 10 GB, so it is going to request the cluster manager for 11 gigabytes of data for this container. Yeah, so I hope all of that makes sense. It has become a little messy with all these numbers over here, but I hope this gave you clarity on how the numbers are divided between each portions of the memory. Okay, so now we are going to talk about unified memory. And this portion of the memory, the execution and the storage memory together, is called the unified memory, as we've seen earlier as well, right? And the reason why storage and execution together is called unified is because of dynamic memory management strategy of Spark. Simply meaning that if execution wanted more memory, it can simply use some of storage memory, and if storage wanted more memory, it could simply go ahead and use execution's memory. But there is a priority which is given to execution memory, because all of the important operations like join, shuffle, sorting, and group by, they happen in the execution memory. So basically what I mean to say is that this slider that you see over here, this slider is movable. It can go up or it can go down based on whichever portion needs whatever memory. It can go up and down. Yeah. So I wanted to talk a little bit about how the scenario was before Spark 1.6 and after Spark 1.6. So before Spark 1.6, let's assume that this whole space is for the unified memory. It's for the unified memory, and what we see over here is that the space that was given to execution and storage memory was fixed. So this was fixed, right? The bar was not movable. You cannot move here and there. So if execution needed more memory, let's say whatever memory it had, it was already full, and if it needed more memory, despite storage being empty over here, this portion is empty, despite storage being empty, it won't be able to use this portion of the memory, and this is a big waste of memory and space that is available, right? So after greater than equal to Spark 1.6, this slider that you see over here became movable, right? So it can move accordingly based on the needs of execution and storage memory. So let's look at a few rules which would define how the slider could move and where it could move, right? So let's imagine that execution needed more memory. Yeah, so this was the extra memory that it needed. So what it could do is that if there was available memory if there was vacant memory, and we see here the storage is not using this memory, it can simply go ahead and utilize that portion of the memory. Yeah. So this portion of the memory that is not being used by storage, it can simply be used by execution. And you see that execution has already used some portion of storage memory. Yeah. Now coming to the second example. Now let's say that storage also has some blocks. Storage is occupied until here and execution is occupied until here. Yeah. Now in this case we see that execution needs more memory. So execution is saying that, hey, I need to do some more joins and some more shuffles and aggregation, give me some more memory. Yeah. So in that case, what storage is going to do is that storage is going to take some of its blocks. Yeah, it is going to take some of its blocks, and then it is going to evict those blocks in order to make room for execution memory. And this eviction is going to happen using the LRU algorithm. The least recently used blocks are going to be evicted. So this space that you see over here is now going to be available, and then it is going to be used by the execution memory. Yeah. Now coming to the last case, where we see that storage has indeed occupied a lot of memory, right? And execution is until here. Oh, sorry. Execution is until here, right? And storage has occupied until this very part, from here to here. Yeah. Now whatever jobs we are running, whatever program we are running, in that program we need to cache a few more objects, right? We need to cache a few more objects, and in order to cache a few more objects we need more of storage memory. So storage is basically saying that, hey, I need more memory, give me more space, right? So then in that case, because execution has a priority and because critical operations are executed within execution memory, none of the execution blocks are going to be evicted. It is storage who has to evict its blocks based on LRU, and then this space, whatever this space is going to be freed up, and then storage is going to store the new blocks, the newly cached data over here in this block over here. And this is simply because execution is given priority over storage, right? And apparently what we've also seen is that a lot of us do cache a lot of times, right, without properly understanding if a particular piece of code needs caching or not, right? For example, there is the data frame, and that data frame is never going to be reused, but we still cache that data frame. So there's no point caching such data frame, right? And that also emphasizes on the fact that why it is important to give more priority to execution memory, right? Because again, all critical operations are happening on execution memory. You can for sure cache things again on the storage memory. So in this case, to reiterate, storage would have to evict its own blocks and then make space for more memory, and the new blocks that are going to be cached is going to be fitting in over here. Yeah. Okay, so now before talking about the off-heap memory, I wanted to reiterate that the on-heap memory is the place where majority of Spark operations takes place, right? All kind of joins, aggregations, shuffles, sorting, and all of that, right? And the on-heap memory is managed by the JVM. Now, in the event that the on-heap memory is full, in the event that this is full, there is going to be a garbage collection cycle, right? So there is going to be a garbage collection cycle, and the primary use case for this is that it is going to pause the current operation of the program and then it is going to clean up all of the unwanted objects in order to make room for the program to resume, right? So this pauses that GC does from time to time may take a toll on the performance of the program, right? And it is in this case where you may use the off-heap memory. So it is in this case where this may come in very useful. Yeah. Now the off-heap memory is managed by the operating system, and therefore it is not subject to the GC cycles, the garbage collection cycles on the executor. Yeah. However, a very important point to note is because it is not subject to the garbage collection cycles on the executor, it is the Spark developer who has to take care of two things. The first one is the allocation, and the other one is the deallocation of memory. Again, this adds complexity to the overall process, but it is really important in order to avoid memory leaks. Hence, the off-heap memory is supposed to be used with a lot of caution because there's additional responsibility on your shoulders to do the allocation and deallocation of memory. Another caveat of this is that the off-heap memory is slower than the on-heap memory. The on-heap memory is the closest to Spark. However, if Spark had two options, the first one was to spill to disk, or the other option was to use the off-heap memory. A better choice would be to use the off-heap memory because writing to disk would be several orders of magnitude slower. Yeah. So I believe that gives you a little bit of overview of what the off-heap memory is and how it can be used. And in order to use it, you basically have to first spark dot have to set spark.memory.offheap.enabled to true. The first one has to be set to true, and then you specify the size of the off-heap memory. And as I explained earlier, it is a good start to maybe start with 10 to 20% of your executor memory. Yeah. It's great to see that you've reached the end of the video. So to summarize, we've covered executor memory management, we've covered the executor memory layout, we've also talked about the unified memory, what is unified memory, why is it called unified, and the rules that decide the movement of the slider between storage and execution memory. And lastly, the off-heap memory. So I hope all of that made sense. And if it made sense, please don't forget to subscribe to my YouTube channel, like the video, share the video. Again, thank you so much for watching.